All right. Thank you for introduction. My name is Michi Sababa from the JAXA, Japanese Space Agency, and my talk is modeling study of the cohesive granular material like a lunar regular simulant called as FJS1 from Japan. Next slide, please. Okay, please go ahead to the movies. Please, maybe stopped. So this is one of the example what we did. So in JAXA, the validation between the microgravity experiment and CFD DEM coupled simulation like that. So this is the one of the example, and we used Tohoku silica. That is a non-cohesive material, very like relatively larger than the lunar regular simulant. So the mean diameter is 0.5 millimeters. So the like a ball-like material. So we already made a good agreement between them, and under vacuum and the microgravity experiment. Next slide, please. Here is the next example, the same sequence compared to the previous slide, and same material, same environment, but there are non-drop situations. So I mean, under the environment like that. We also use the same simulation model based on the CFD and the DEM coupled simulations. And we also made a good agreement between them. So in terms of the scattering behavior, crater formation in the from the transitional point of view. Yeah, this is one of the good video from our side. Next slide, please. But we now struggle to solve the next difficulty to the such a non-cohesive the cohesive material like a lunar simulant like that called as FJS1 from Simis Corporation they made. So the FJS1 is a very similar material like the BP1, the lunar simulant in US. As you know, the tiny particle size and the sharp shape in each particle made a strong characteristic of their cohesive properties. So compared to the Tohoku silica, that is what we did. So this is such a cohesive property related to the significantly influence the scattering behavior, both not only the scattering behavior, but also the crater formation. So in this case, so far, we cannot succeed to simulate the CFD-DM capital simulation because of the computational cost and the modeling difficulty like that. Okay, next slide, please. This is one of the summary slide, what we did in terms of the non-cohesive material. We chose the Tohoku silica number 5 as a non-cohesive material, and we finished some of the microgravity experiment. This experiment is under vacuum and microgravity environment in the chamber. So we dropped the chamber. And we also finished the simulation, some of the simulation, and made a validation between them. So through this process, we found out how to modeling between the particles and what parameter we needed to be chosen. So like some of the parameter mu r equals 0.5 like that. So based on this simulation, we probably predict such a PSI issues, but this solution is strongly limited to the non-cohesive material. This is not the same situation for the lunar landing. Next slide, please. And moreover, the microgravity experiment and the CFD-DM simulation is a heavy cost. So to do that, so that's why we now start to do the complementary experiment under 1Z environment and the simulation to determine the DM parameter without such a heavy cost. I mean, the microgravity experiment and the CFD-DM simulation beforehand. So once we finish such a situation, we can determine the DM parameters to predict the PSI issues. The next slide, please. Moreover, we also need to solve the DM parameter process with the cohesive materials. This is one of the next difficulty to determine that. So so far, we also struggle to determine such a parameters with the even non-cohesive material. So and tau silica is larger and the non-cohesive material, even the larger and the non-cohesive material compared to the FGS1. So we needed to pay attention to such a cohesive properties even under the environment. Next slide, please. Okay, so this is the optional future aspiration. So as like have such missions, we human being cannot find out what kind of the shape on the about the Ryugu and what kind of the border on the surface on the Ryugu as well. So and scientists, on the other hand, scientists can make a simulant copy material on the Ryugus, so probably based on their observation and the limited condition. So on the other hand, engineers' viewpoint, we engineers need to decide when and where touch down on the surface. So once we've made such a procedure to determine the DM simulations, we will have another space mission like HAPSA-2 and the touchdown and landing on the surface, including the lunar environment. Next slide, please. Here, okay, please go ahead to the video. Play the video, please. So this is one of the 1D environment experiment. So like that, the dynamic angle of ripples. So the particle interlocking frees to such a large dynamic angle compared to the non-cohesive material at the left side of the figures. So almost 90 degrees. So it's difficult to reproduce the large dynamic angle ripples only by the tuning the coefficient friction and cohesion in the DM simulation in the right figures like that. Next slide, please. To reproduce the large angle of ripples, this is one of the ideas to simulate that. So by using the cluster model, so to mimicking such an properties. So this is one of the example to do that. But it's now possible to create such a the cohesive materials property under one's environment. But cluster model is also have the difficulty to determine the parameter tuning. based on the DME simulation, even only. So how much clusters we need to be solved or something like that. So we are now struggling to the such a DME simulation. Okay, this is a summary viewpoint from my presentation. Thank you and hearing and pay attention to that.